Turbine meters, precision flow sensing with calibrated performance and diagnostic integrity, performance requirements and calibration precision. Turbine meters must be selected to deliver high linearity and repeatability across a wide operating range, with performance characterized by traceable calibration. Each meter must achieve a linearity better than plus 0.25% over a 10-to-1 flow range at the specified operating viscosity. Initial calibration should be performed using a liquid matching the process viscosity. However, if unavailable, water may be used with manufacturer-provided viscosity correction data. Repeatability under stable conditions must be better than plus 0.05% of mean pulse count. This performance must be verified at both minimum and maximum flow rates, as well as across several intermediate points throughout the operating range. Calibration checks must be conducted at both the manufacturer's facility and at site conditions to validate field performance against certified laboratory results. Flow conditioning and meter run integration. Turbine meters must be installed with appropriate upstream and downstream pipe lengths and flow conditioning elements. Minimum straight pipe lengths of 10 internal diameters upstream and 5 diameters downstream must be maintained. Flow straighteners or meter tubes must be included where necessary to eliminate swirl and profile distortion, ensuring the rotor is exposed to a symmetrical velocity distribution. The entire meter run must remain liquid-filled under all flow conditions, including static or zero flow states, to prevent gas pockets or cavitation that would compromise pulse accuracy and meter longevity. Pulse generation and signal integrity. Each turbine meter must be fitted with dual magnetic pickup coils and signal preamplifiers. These dual pickups provide redundancy and allow pulse integrity checks through real-time comparison of signal trains. The design must permit removal and replacement of the pickup coils without removing the meter body from the line. Connections must allow for tamper-resistant sealing in accordance with regulatory requirements. Pulse outputs must be clean, distortion-free, and compatible with downstream microcomputer pulse input thresholds. Shielded cabling and signal isolation techniques must be used to prevent false triggering from electrical noise or grounding errors. K-factor management and meter factor tracking. Each turbine meter must be assigned a unique calibration factor, K-factor, representing the number of pulses per unit volume. This factor must be established during initial calibration and manually entered or digitally downloaded into the associated stream microcomputer. The microcomputer must also retain the previous K-factor value to support traceability and audit review during meter factor updates. Meter factors must be recalculated during proving operations, and any significant deviation from prior values must trigger an operator prompt and require confirmation before the new factor is committed. Mechanical construction and maintenance accessibility. Turbine meters must be designed for long service life in continuous flow applications, with rotors, bearings, and internal components selected for durability under the fluid's chemical and thermal properties. Meters must include provisions for inline removal and reinstallation without disturbing adjacent piping. Flanges and body connections must support safe removal and resealing. All wetted materials must be chemically compatible with the process fluid and rated for the maximum pressure and temperature expected in the line. Meters must include provisions for identifying rotational drag or obstruction, such as vane failure detection systems or rotor speed diagnostics. Vane failure detection and redundancy. Each turbine meter must be equipped with mechanical or electronic means of detecting rotor or vane failure. This function must operate independently of the primary pulse train and generate a diagnostic alarm if abnormal rotational behavior is observed. Detection mechanisms must be sensitive to conditions such as jamming, disintegration, or fluid-induced overspeed, providing early warning before flow measurement becomes unreliable. Turbine meters are the core primary measurement element of the Fiscal metering system. Their selection, calibration, and installation must ensure traceable, reproducible accuracy under actual process conditions. Each meter must be matched not only to flow and fluid properties, but also to system-level diagnostic requirements, enabling continuous verification and real-time performance assurance. Strainers, debris protection and flow assurance for measurement integrity. Strainers are essential upstream components in each metering run, serving to protect the turbine meter from mechanical damage caused by particulate matter, corrosion products, or pipeline debris. Each metering stream must include a single basket strainer constructed from stainless steel, equipped with a removable mesh insert matched to the particle size tolerance specified by the turbine meter manufacturer. The strainer must feature a flanged quick-release closure, ideally with a davit arm or hinged mechanism, to facilitate easy removal of the basket without requiring extensive disassembly or special tools. Vent and drain ports must be included to safely depressurize and drain the housing prior to opening. These connections must be flanged with proper sealing and pressure rating consistent with the process line. Differential pressure monitoring must be installed across the strainer to detect fouling and signal the need for cleaning. This may be accomplished through analog transmitters, pressure switches, or digital sensors interfaced with the control system. Alarms must be generated when differential pressure exceeds predefined thresholds, preventing bypass or performance degradation of the turbine meter due to flow obstruction. Strainer housings and internal components must be rated for full design pressure and temperature and constructed from materials compatible with the process fluid. Internal surfaces should be smooth and free of corrosion traps to minimize pressure drop and ensure ease of cleaning. Flow straighteners, flow profile stabilization for metering accuracy. Flow straighteners are mandatory in each metering run to eliminate swirl, turbulence, and asymmetric velocity profiles that would otherwise affect turbine meter accuracy and repeatability. The straighteners must be installed directly upstream of the turbine meter in accordance with the required meter tube lengths to condition the flow before it enters the rotor chamber. Construction must follow best practice geometries such as tube bundles, vane plates, or perforated flow conditioners with minimal additional pressure loss. The design must be fabricated from corrosion-resistant materials, ideally stainless steel, and matched to the internal diameter of the meter run to maintain laminar alignment. Welds and internal surfaces must be free of burrs, protrusions, or roughness that could disrupt the flow. Straighteners must be designed for long service life and minimal maintenance, with secure mounting that prevents vibration, fatigue, or misalignment under varying flow rates. The effectiveness of the flow straightener must be validated as part of the overall meter calibration process, ensuring that its contribution to flow stability supports the stated meter linearity and repeatability across the full range of operation. Flow control valves, dynamic regulation and proving stability across operating range. Each metering run must include a dedicated flow control valve to regulate the flow rate through the turbine meter and enable stable conditions during proving, turn down, and transitions between meter runs. These valves are typically pneumatically actuated for precise responsive control and must include a side-mounted, declutchable handwheel for manual override in case of actuator or air system failure. Control valves must be capable of modulating smoothly from minimum to maximum flow without introducing hydraulic shocks or oscillations. They must also provide rapid shutoff and fine throttling to support proving sequences and ensure consistent proving volume delivery. The valve actuation mechanism must include position feedback for closed-loop control and be interfaced with the control system for remote set point input and status monitoring. Sizing of the flow control valve must be based on accurate flow coefficients and pressure drop characteristics in accordance with established sizing equations for incompressible liquids. The valve must maintain control authority under all expected flow conditions, including low flow proving, partial load, and full capacity operation. Valve bodies and trim must be manufactured from materials compatible with the fluid and suitable for the design pressure and temperature range. The preferred installation position is downstream of the turbine meter to reduce upstream disturbances and preserve meter accuracy. Actuators must be sized with sufficient margin to overcome differential pressure and ensure positive sealing. Properly selected and configured flow control valves enable flexible, safe, and stable operation of the metering system, especially when adjusting for process fluctuations or initiating calibration cycles. Their performance directly influences measurement repeatability, prover compatibility, and system responsiveness. Temperature measurement, high-resolution thermal sensing for volume and mass compensation. Temperature measurement in each metering run is critical for accurate volume correction and mass flow computation. All temperature sensing must be performed using electrical resistance thermometers, specifically PT100 platinum RTDs, resistance temperature detectors. With a resistance of 100 ohms at 0 degrees Celsius and an alpha coefficient of 0.00385 millimoles per degrees C. These elements must meet Class A tolerance standards to ensure precision across the operating range. The RTDs must be interrogated directly by the stream microcomputers using a 4-wire connection method. This configuration eliminates the impact of lead resistance and supports precise calibration without introducing additional field transmitters. Measurement spans should typically cover 0 degrees Celsius to 100 degrees Celsius, although narrower ranges may be used when process stability allows, improving resolution. Each RTD must be installed in a flanged thermowell that permits safe replacement or calibration without depressurizing the system. A second thermowell must be installed adjacent to the primary, positioned on a different radial axis to avoid vortex-induced fatigue. This secondary well enables on-site verification using a high-accuracy reference thermometer. All thermowells must be constructed from corrosion-resistant material, with a minimum internal bore of 6.5 millimeters to accommodate precision mercury in glass thermometers or certified electronic probes. If specified, the manufacturer must supply 2 certified reference thermometers with an accuracy of better than 0.1 degrees Celsius for calibration and verification purposes. Redundant pressure monitoring for real-time compensation and calibration integrity. Each metering stream must include both electronic pressure transmitters and mechanical pressure gauges for monitoring operating conditions and supporting dynamic flow compensation. The electronic transmitters must be of the smart type with 4 to 20 milliamps analog output and optionally with digital communication capabilities for diagnostics and configuration. They must meet high precision tolerance classes and maintain calibration stability over extended periods. Transmitters must be mounted with 3-valve manifolds that include an additional impulse line connection. This allows connection to a deadweight tester for calibration checks without removing the transmitter from service. When specified, a certified deadweight tester must be provided with uncertainty better than half the accuracy of the transmitter under test. To support proving and calibration operations, transmitters must be installed at points that represent the true process pressure with minimal lag or dampening. Board-on tube-type pressure gauges must be installed locally on each stream with a minimum dial size of 100 millimeters for clear visibility. These gauges provide redundancy, enabling cross-checks during operation and maintenance. All pressure instruments must be housed in enclosures rated for outdoor installation and constructed from materials compatible with both the process and environmental exposure conditions. Installation must ensure vibration isolation, easy access, and safe operation during pressurization or draining. Density measurement, real-time mass conversion and cross-validation with dual densitometers. Each Fiscal metering system must include a dual vibrating tube densitometer system installed on a slipstream taken from the metering station header. This configuration allows continuous density measurement of the process fluid under representative conditions without interfering with the main flow path. The use of 2 densitometers operating in parallel enables real-time comparison and fault detection. A deviation between the 2 sensors beyond a specified threshold, typically 0.5 to 1.0 kilograms per milliliter, must automatically trigger a system alarm and isolate the faulty measurement. The exact deviation limit is to be set based on process fluid characteristics and operational requirements. Signals from the densitometers must be transmitted digitally or as analog values to the metering microcomputers, where they are used to compute mass flow and to perform volume to mass conversions. The densitometer system must be capable of operating within the full pressure, temperature, and chemical exposure ranges of the process fluid. When specified, a precision reference densitometer must be supplied for calibration verification with certified uncertainty better than half that of the field instruments. The calibration procedure must follow recognized industry standards and ensure repeatability under flowing conditions. Installation must include all necessary bypass lines, isolation valves, and drains to allow calibration, flushing, or replacement without interrupting the metering process. All wetted parts must be constructed from corrosion-resistant materials suitable for long-term exposure to hydrocarbons and any associated contaminants. Water cut measurement. Continuous monitoring of water content for net oil determination. Each fiscal metering station must include a water cut measurement system to quantify the water and oil content within the flowing stream. Typically, 2 water cut sensors are installed and operated in duty standby mode. The station microcomputer must automatically switch to the standby sensor in the event of a fault in the primary device. For applications where water content data is only used for operational monitoring, not for fiscal net oil computation, a single sensor may suffice. Water cut sensors must be capable of accurately measuring water content in the range of 0 to 5% by volume with an absolute accuracy of 0.2%. The output signal must be 4 to 20 milliamps analog, scaled linearly across the sensor range, and transmitted directly to the station microcomputer or DCS for use in net oil calculations or alarm logic. When required, a precision laboratory-grade water cut analyzer must be supplied for calibration reference purposes. This analyzer must be certified with an uncertainty better than half the rated accuracy of the inline sensors. Although real-time water cut readings provide immediate feedback, contractual calculations of net oil quantity typically rely on composite sample analysis. As such, the role of the water cut meter is twofold. It offers operational awareness and acts as a supporting input to net quantity algorithms, subject to validation against sampled laboratory data. Installation must ensure representative measurement by positioning the sensor in a well-mixed section of the stream, typically downstream of flow conditioning and upstream of sampling. The measurement loop must allow for isolation, flushing, and sensor replacement without process interruption. Materials must be fully compatible with crude oils and any expected contaminants or additives. Sampler. Representative composite sampling for laboratory analysis and custody validation. A flow proportional automatic sampling system must be installed on the metering station's inlet manifold to collect representative liquid hydrocarbon samples over a defined measurement period. The system must be of the grab type, actuated by discrete impulses from the station microcomputer. Each impulse must trigger a sample extraction event, with the cumulative sample forming the basis for quality analysis and net oil computation. The sampling system must conform to recognized international standards for petroleum sampling and operate in a manner that ensures each grab is proportionate to the totalized flow volume. A console-mounted indicator must display the number of samples taken, and a voltage-free contact output must verify that impulses from the microcomputer are being properly received and executed by the sampler solenoid. Sampling must occur at constant pressure to preserve fluid homogeneity and avoid phase separation. The system must include temperature control via heat tracing or insulation as needed to maintain a stable viscosity and prevent sample stratification or wax dropout, especially for heavy crudes. The sampler's collection container must be designed for easy removal and transportation to a certified laboratory with appropriate sealing provisions to prevent tampering. Drainage and flushing provisions must be included to clean the sampler between batches, ensuring that each collection cycle is free from contamination or residue from previous samples. System reliability, timing precision, and accurate flow synchronization are critical, as the composite sample often forms the official reference for contractual custody transfer and product quality reporting. Sampling systems must therefore be integrated tightly with flow computation logic and alarm systems, with manual override and validation functions available through the station interface.